All right, that's much more better. Okay, so I've already started my recording. All right. Okay, so we're gonna do a quick recap on waves, lights, and optics. So today we are hopefully gonna cover these few things. All right, determine wave frequency, wavelength, and also if we manage to go into, we're gonna go into resonance and also damping today. All right, so let's proceed. Okay, a quick recap on what waves is about. Waves is a vibration or oscillation of a particle that transfers energy without transferring matter. So, wave, the first thing is it's a vibration or oscillation. So, a very quick example, let's see where are my simulations. Okay, so I'm just going to let that run for a while. Okay, so without transferring energy or without transferring matter, it could be any energy, light energy, sound energy, water energy, sound wave and all that. The energy could be kinetic and all kinds of different types of energy, but the most important thing is that the matter will not move, which means that the particle does not move. So in your syllabus there are two types of waves, okay? Progressive wave, stationary wave, mechanical wave, and electromagnetic wave. So I'm going to focus on progressive wave and stationary wave because I think it's a little bit confusing. Progressive waves is whereby the profile of the wave changes with time. This first sentence is the definition from your textbook. All right, the waves where the profile of the wave changes with time. An example, it means that the wave will keep moving away from the source of vibration. So, an example of progressive wave is transverse wave and longitudinal wave. Okay. Stationary wave, from the definition in the textbooks, is whereby the profile of wave does not change with time. A profile that doesn't change with time is example is the wave that is produced in the musical instruments, whereby it just move up and down only. All right, progressive wave it can actually move further away from the source of vibration. All right, I'm a little bit distracted for a while because I need to take the simulation out for you all to see. Okay, be very very quickly to open it. I actually opened it already just now, but somehow my laptop crashed, so that was a little bit scary for me lah. Okay, now so for example, the pencil is placed on a spring and it's moving up and down. So in a way to say that the pencil is vibrating or oscillating, and when this pencil pass by on a moving paper, all right, it is creating waves over here. All right, I want you all to ignore all the numbers that's moving along and just focus with the pencil and the pattern that is producing out. So this example, all right, whereby the pencil is vibrating up and down. All right, so it's moving up and down, so it's changing from kinetic energy to gravitational potential energy. But the object, all right, the metal, which is the pencil, is just moving up and down above itself. So this can consider as an example of a transverse wave. Okay, and progressive wave means that the wave is moving away in time. All right, so this is an example of a progressive wave. Okay, stationary waves is the wave profile does not advance, the energy is not transferred from one end to the other end, it just keeps on moving up and down, all right, as though that it's a wave that is oscillating up and down. It's produced by overlapping two progressive waves with equal amplitude and frequency, but moving in opposite direction. Right, so an example of stationary waves is the wave produced by a musical instrument. I remember showing this stationary waves to your last lesson 2 weeks ago. Okay, so what is transverse wave? A very quick recap again. Transverse wave is the vibration of the particles in the medium. It's perpendicular to the direction of the propagation. So if I take a slinky spring, all right, remember slinky spring is just an apparatus for you all to identify, all right, for us to show what is a transverse wave and longitudinal wave. Slinky spring is not a type of wave, it's just an apparatus in lab. So Transverse wave means that, let's just say the hand moves the slinky spring up and down, right? Moving side to side movement. So the wave, you can see that the energy of the wave is moving towards the right hand side. So this is the direction of the wave propagation. The red color line shows the direction of the wave propagation. And then if there's a particle on the slinky spring, if I tie a string over there, that string or the particle will just move up and down, up and down. So that's the direction of the vibration of particles. So transverse wave is the vibration of particles in the medium, which is perpendicular to the direction of the propagation of the wave. The wave is moving on x-axis, but the vibration of the particles is moving on the y-axis. Okay, so the motion is actually right angle to the direction of the wave travels. An example is water wave, light wave. Okay, electromagnetic wave is also a transverse wave. What is electromagnetic wave? We will learn at the end of the chapter, but for the Form 5, you all would have already known that electromagnetic wave is a combination of electric field and magnetic field. Okay, so next, longitudinal wave. Longitudinal wave is whereby we take the slinky spring and we make a front and back movement at the slinky spring. Okay, so when we make a front and back movement, when you push it in front, it will cause the slinky spring to refract. And then, compress, not refract. This sentence is a little bit wrong already. Okay, this one is not supposed to be refract. This is compression. Okay, and then when we move the slinky spring backwards, and it will actually cause rarefaction. So this compression and rarefaction will move towards from the source of the vibration, which is the hand location, all the way towards the other end, which is a fixed end. So the direction of the wave propagation is on the x-axis, and then the particles, if it's tied at one position, the particles will move front and back as well. So it is also on the x-axis. So longitudinal wave is whereby the vibration of the particles in the medium is parallel to the direction of the propagation of the wave. So which means both of it is on x-axis or both is at y-axis. Okay, it is it is parallel to each other. So an example of that would be sound wave. And to show you the simulation of a longitudinal wave and transverse wave would be this. All right, so you can see a series of compression. All right, here you can see a series of compression moving towards the right, and then this location is considered as rarefaction. Okay, so this is longitudinal wave. The source of vibration is on the left. All right, as you can see, it gets pushed towards the front, towards the back. So when it pushes forward, it will cause compression, and that's how we see the wave energy moving towards the right. Okay, and then when it's pulling to the back, it causes rarefaction. Then at the bottom part, this is a transverse wave. A transverse wave means that the profile is moving towards away from the source, and then we can see that the direction of the wave is also moving towards the right, but the particles will move up and down. Okay, so as you can see, let me pause this for a while. As you can see, there's one word here called wavelength. All right, wavelength I did introduce last week as well, and I'm gonna just quickly refresh you. Wavelengths means the distance from a crest to another crest, and for longitudinal case, it's actually from a compression to another compression area. So that wavelength means the distance from one position to another position of the same phase. Okay, so that is wavelength. We will recap that in a short while again. Okay, so that is transverse wave and longitudinal wave. Okay, so similarities and differences between transverse and longitudinal wave. We have, where is my, okay, so transverse wave and longitudinal wave, first and foremost, they are both progressive wave. Okay, it's not written over here on this slide. Both transverse and longitudinal wave are progressive wave. It means that the process of transferring energy from one location to another location, it is produced by an oscillating or vibrating motion, but it does not transfer matter, which means the particle will not transfer, they will not move away. Obviously, this is an ideal case lah. Okay, transverse wave, right? The direction of the vibration of the particle is in the medium is perpendicular to the direction of the propagation. Meaning means that if the wave is moving to right, this is the wave direction. The particle is moving on the y-axis. Okay, so that's for transverse wave. Example, water waves and light waves. Longitudinal is whereby the vibration of particles in the medium is parallel to the direction of the propagation of wave. Meaning means if the wave is moving away towards the right on the y-axis, okay, the particle on the wave is moving, oscillating about its position at the x-axis as well. So that's why it's considered parallel and longitudinal wave. An example so far that I know right now, up to right now, sound wave is the only longitudinal wave. All right, so far that I know until my knowledge lah. Okay, so far are you guys okay with this recap? Hopefully, yeah. Okay, so another recap, because this one I think I went quite fast last week. Form 4, if you think too fast and you don't understand as usual, remember to message me inside the chat box. Okay, now explain the characteristic of a wave. Now, if you were to recall just now the simulation that I showed you, this simulation, when the pencil is vibrating or oscillating above and below due to the spring, okay, it causes a wave to be shown. Okay, Form 5, you would identify this wave as something that you have. Okay, elaboration on how sound wave is longitudinal. Okay, give me a quick minute. Let me finish explaining this first. So, okay, tiba-tiba I sudah KO already. Okay, so Rabika says need a little elaboration on how sound wave is a longitudinal wave. So since due to that, let's see. Let me quickly just find back one PowerPoint. Let me get my sound wave. All right. Okay. So how sound wave is a longitudinal wave. Okay. So for example, let me just show you this. Okay. So you see, let's just say a tuning fork. Okay, a tuning fork, I think those who actually learn music, you would be very familiar with this. So a tuning fork, when it is being hit, okay, you can hear the sound over there. So when the tuning fork hits, right, it will actually vibrate the air particles around them. So I'm going to use a very simple explanation here. Okay, how does sound wave act as a longitudinal wave? So the longitudinal wave disturbs the particle A, which is at this position, resulting a periodic pattern of compression and rarefaction. It's similar to the stinky spring. So sound wave can be described using, okay, this one ignore first. Okay, explanation. All right, considering a vibrating tuning fork or a speaker, okay, when the blade of the tuning fork moves towards the right, it compresses the air molecules, shifting it towards the right. So when it moves towards the left, it drags a little bit of air molecules and shifting it to the left, which causes the rarefaction. So very quickly, let's see here. Okay, so let's just say this is where we have a tuning fork over here. All right, when the tuning fork moves towards the right, okay, when the tuning fork moves towards the right hand side, let's see here, this part. When it moves towards the right, it will actually push the air particles around it. Okay, when it pushes the air particles around towards the right, it compresses the air particles. So when it compresses the air particles and the energy is from this position, so the energy will push the air particles towards the right hand side, compressing some air particles which is initially static at that moment, and then the air particles will hit each other. So when it hit each other, the energy will get transferred. Then after that, when it moves backwards, okay, when it moves backwards, it drags a little bit of the air molecules nearby, shifting the air molecules at the side there to move towards the left hand side, which causes the rarefaction part. Okay, so here, as the blade, all right, the tuning fork blade vibrates continuously, a series of compression and rarefaction is being produced. At the region of maximum compression and rarefaction, the particles is not vibrating at all, where the displacement, okay, this one you don't have to bother lah, okay, this statement tak payah bother. Okay, the compression region, the particles gets closer, hence the pressure in this region is greater and the collision is obviously stronger. Then rarefaction, the particles become further apart and the pressure in this region becomes less than the atmospheric pressure. All right, so at the very least, at the front part, okay, considering the vibration of the tuning fork, when the blade moves towards the right, it actually compresses the air molecules. All right, that's the compression part, and then it will get transferred towards the right hand side. And then the other part, it will rarefract when the tuning fork is being moved away. All right, it will drag a bit of the air molecules, shifting it to the left, causing the rarefaction part. So this, as the series continue, all right, as the series continue, you will keep getting a compression and rarefaction, compression and rarefaction. The compression part will actually transverse because one air molecule hits another one. All right, this is compressing. When they hit each other, there's a compression there. And then when it rarefracts to the back, these air molecules will hit another one towards the right side. So it will continuously cause it to move towards the right end. Okay, so that is how sound wave is considered as a longitudinal wave. So is my explanation okay for you?
Yeah, Che, I understand better now.
Okay, so I'm going to this few parts that I tick. If you all screenshot, please just until this part lah. Okay, the rest kat bawah tak payah. Since you asked me this, I took my old syllabus out. Okay, so now let's continue here. All right, explaining the characteristic of a wave. Now, this straight line here is actually called the equilibrium position. At the very beginning, when a wave is not moving at all, okay, if let's just say, for example, we talk about this oscillating pencil, okay, if this oscillating pencil, there is no movement at all, okay, the pencil will, if this paper continues on running, but this pencil is not oscillating, the pencil will draw a straight line on the x-axis. This is an equilibrium position for the pencil. Okay, so if the pencil starts to oscillate up and down due to the spring, okay, it will go from the equilibrium position to the maximum, down to equilibrium, and then back to the minimum position. I'm going to stop it there. All right, so the position from equilibrium line up until the maximum point, that is actually what we called as an amplitude. From the equilibrium position up to the maximum point, the point at the max is what we call a crest or a peak. All right, and the distance going upwards, that's what we call amplitude. And then as well, the minimum position, we call it as a throw. All right, so from the equilibrium position down to throw, that is also amplitude. Okay, so from the equilibrium to the maximum point or the peak, from the equilibrium to the minimum point or the throw, that is the amplitude. Okay, so these few parts you have to be aware of, because after this, whenever we talk about any phenomena at all, these are the characteristics that we will have to say, that we will have to talk about. Okay, so that is the y-axis. Let's talk about the x-axis. From the position of the equilibrium to the other end, after it has already oscillate from one end to the other end and then back to the equilibrium position, depending on what is and the x-axis. Okay, if it's distance, measuring distance from this position until this current position. Okay, I don't have my writer on this. From one end to the other end, this position, this is what we call as a wavelength. All right, from a position to another position. Okay, that is from the crest to the crest, for example, easier to see. From one crest to another consecutive crest, consecutive means directly the next one. The distance between these two crests are known as a wavelength. Okay, so let's see. All right, this is the definition from the textbook. If the exam question asks any definition, it has to refer back to the textbook. So, definition amplitude is the maximum displacement of a particle from its equilibrium position. So, that is what it meant. From the equilibrium position, which is the y axis, up until the maximum, that is the amplitude. Period is the time taken for a particle to make one complete oscillation or a source to produce one complete cycle of wave. Meaning means, again, back to the simulation. Okay, again, back to this simulation. All right, I'm just going to virtually manually count this. All right, for it to take one complete oscillation, I play this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so from here to this position, it took 10 seconds. So this is one complete oscillation of a wave, and it took 10 seconds. So that is the meaning of period. All right, time taken for a particle to make one complete oscillation, all right, or the source to produce one complete cycle of the wave. So that's the meaning of period. Frequency is the number of complete oscillation made by a particle or number of cycles of wave produced by a source in 1 second. So just now the period was, let me just scribble this. Okay, just now that simulation, the period was 10 seconds. So how many oscillation, all right, how many complete oscillation did the simulation did in 1 second? So in order to find out, I take frequency is 1 over period, so 1 over 10. So the simulation only did one complete oscillation. Sorry, 0.1 oscillation, all right, in 1 second. So that's what it meant by frequency. Okay, frequency formula is from here, it's F over 1 over capital T. Wavelength, I already mentioned, the distance between two consecutive points in the phase. Wave speed, the distance traveled per second by a wave profile. Do you all still have to ask me to, do I need to recap you guys how does wave speed being produced? I think okay, right, for wave speed?
I think you can recap.
The rest?
Yeah, sure. Yeah.
Okay, give me a quick minute. Let me get. Okay. Now, for a wave to carry out one complete oscillation, right? So this is the equilibrium position. So this is one complete wave. Okay. So this is what we considered as one complete oscillation from the equilibrium to the max point to the equilibrium and then down to the throw and then back to equilibrium again. So this is one complete oscillation. Okay, so the time taken for one complete oscillation is known as period, capital T. Okay, the distance for one complete oscillation is known as a wavelength, lambda. Now, in our previous syllabus, all right, in from two blood in forces and motion, all right, we talk about speed. Okay, in terms of magnitude only, in terms of speed's definition is distance over time. So when we are talking about wave, we will talk about wave speed. So when we talk about wave speed, it means how fast the wave is moving. So in order to calculate wave speed, it's actually similar to our definition for speed. So wave speed means how fast the speed is moving in one complete oscillation. So the distance here in wave is actually one wavelength. All right, the distance for one complete oscillation is a wavelength. So wave speed is wavelength lambda over the time taken for one complete oscillation is known as period, capital T. So wave speed formula is wavelength over period. Now, obviously, normally when we memorize something, we try not to memorize over, right? Lambda over T or lambda divided by T. So we normally use it in a single, uh, uh, it's at the same level. So this formula, wave speed, is the second formula. The first formula in wave is frequency equals to 1 over period, which I just used just now. Okay, so when I put period here, 1 over period, I can substitute it with what we have at the wave speed. So my wave speed can also use the formula of f lambda, where I substitute 1 over t with f. Okay, so this is the second formula in wave chapter. All right, this means that the wave is moving at the speed, all right? The speed of the wave for one complete oscillation is the frequency multiplied by the wavelength. All right, so this is how we got wave speed. It's from the definition of speed equals to distance over time. Okay, so that is how we got wave speed. I hope you guys are okay with that. Can I proceed? Your screenshot already?
Yep. Screenshotted.
Yeah, sure. Yep.
I know nowadays you're very seldom screenshot, but can you please remember one thing? After you screenshot, remember to transfer back to your book.
Okay.
Or else everything also useless. Okay, so with that, I am going to let me rearrange something first. Okay. All right, so I am going to try a few things first before we proceed. Very quickly. Okay. All right, so can you all enter the class point for a while? There are a few exercises. I think need to give you guys some exercises first. So can you all please enter the class point? Can masuk? Tak boleh masuk. I think it's the same code anyway. All right, so I'm just gonna start. If you all want the class point code, it's the link is like the chat box, and then it's normally on the right hand side top corner. Okay. So those of you, you all still can continue coming in. All right, can you please try this? Is it working on your side?
We can see it, but how do we press? How do you enter the answer, Che?
Wait, let me just get it back in. Okay. I'm gonna get my handphone charger since I'm using my own hotspot. So you'll try to answer this question first. So I just want to know what's your answer. I'm curious, how did you count 1.5? Alright, I'm gonna close the submission for right now. Um, what I tried to do at this activity is try to tell you guys why I don't always follow the textbook. Because the textbook, when they ask you to do questions like this, they've forgotten to teach you one important part which they shifted to the third subtopic that is known as the wavefronts. Okay, so I'm just going to save this first and I'm going to go next. Okay, those of you who actually got 1.5, yes, your answer is correct. It is 1.5. For those who did not manage to get the answer, the main reason is because the textbook left out one very important characteristic, all right, at the part where they discuss regarding characteristic of the wave, and they shifted that characteristic to the third subtopic. Okay, so I'll come back to this question, all right, after I finish 3 slides. Okay, so just to show you guys regarding this. Now, first thing first, physically, all right, physically, in real life, how do we carry out an experiment is actually using a ripple tank. Now, a ripple tank is use an apparatus. It's a whole setup that shows how water wave. We normally use water wave because water wave is easier to observe. Light wave, we are all looking at the effect of light wave right now, but it's so difficult for us to observe light wave, and including sound wave. It's very difficult for us to observe sound wave. But thankfully, we have the third wave, which is the water wave, that we can observe very obviously, and that is actually using a ripple tank. All right. So ripple tanks whole entire setup is like this. All right. You have this whole thing is a ripple tank except for this part lah. All right. So this is the actual part of the ripple tank. Okay. And then we have light here. All right. There needs to have a light source, and then we have this the vibrator. Okay. The vibrator at this part, right? There's two kinds of dipper. Dipper means the vibrator being placed in the water, in the water level. So if the dipper is a straight plane like this, it will create out plane wavefronts. But if the dipper is actually a spherical dipper, it will create a circular wavefronts. So a ripple tank is just a device that we use in the lab for us to see the effect of water wave and to investigate the phenomena later on. Okay, so since we are using online as usual, I'm going to be using simulation. Okay, now how does a plane wave? So what you see right now is, if I were to start this in a short while, okay, a single source. What I have right now is a single source. This is a simulation that will show you how does the effect of a ripple tank. So this effect of the ripple tank normally is here, shown at the bottom part here. Okay, whatever, if we were to carry out this experimentally physically, the effect of this part is going to be shown on this simulation. Okay, so I'm just going to play. This is a spherical dipper. All right, so I'm going to start playing this. A spherical dipper, you will see waves like this. This is known as a circular wave. When you have a single spherical dipper, you will have wave like this, and you will see bright and dark, all right, lines that is moving away from the source of the vibration. This is the source of the vibration, all right, that's the single source. And you saw that the wave is moving away from the source, right? The energy of the wave is moving away from the source. Now, but what causes the bright and the dark lines? In a short while, I will show you. Okay, I want to show you how does a plane wave looks like. So a plane wave will looks like this. All right, it's a straight line, so that's why it's called a plane wave. All right, again, we see bright and dark lines. All right, and the energy of the wave is moving from the top. Oh, this is the vibrating source. All right, the vibrating source means this part, the deeper part. Okay, so the deeper part is here on top, and if we were to carry out physically, this is how we are supposed to see. Okay, obviously it's not going to be so slow lah. It's going to be much more faster. Okay, so that is how a image of a plane wave and circular wave looks like. Okay, next is how did that bright and dark line appears. Okay, so for those of you, the part of this bright and dark lines, if I'm not wrong, it's in your textbook under reflective of waves. So you all have to go to subtopic 5.3 there, right? If you have your textbook with you, right, you can see the images over there. So the water, when it actually moves up and down, it will act like a lens to produce a pattern. So when the water wave, when there's a dipper causing it to move up and down, that they will create crest and throw. All right, uniform motion of crest and throw. And here, when it moves crest and throw, what will happen is when you shine light from the top, uniform lights from the top. Okay, it will, if it's a crest, all right, this part is a crest. When it's a crest, when light passes through it, it will focus the light and produce bright fringes. When it's a throw, the minimum part, it will cause the light to move away from the location. All right, so that will actually cause the dark fringes. So the dark fringes means that the position of the wave is actually at the throw, the minimum part. The position, if you see bright fringe, means that's the crest of it, that's the maximum point of it. So again, with the simulation, all right, which means this position, it's the maximum crest, all right, the wave is at the top, and then the dark lines, or what we call is the dark fringe, right? The dark fringe is whereby the minimum position of the wave is located. That's the throw location of the wave. Okay, so what happens here is, if it's not in the textbook, then you all have to just screenshot this or write this down very quickly while I explain. When the water wave crests and throw, the crest, the highest position of the wave, will act as a convex lens. So for the Form 4, you did kind of learn regarding convex lens during Form 1 or Form 2. I've forgotten which year already. But convex lens means that it will, if this is the straight line, it will bend outwards. Okay, so when the light rays comes, right, convex lens is both sides. When the light ray comes into the convex lens, it will, as though that it focuses on the position. All right, so that's convex lens. Okay. My ray diagram sudah terbalik. All right, so convex lens will bend outwards and it focuses at the focus point. So when it's crest, all right, the highest position of the wave, it acts as a convex lens to focus the line towards a position. That's why causing the bright fringes. Then the throw, right, the lowest position of the wave will act as concave lens. Concave lens means the lens bend inwards. Okay, when the lens bends inwards, when the light ray comes out, it will spread out. All right, the light ray will actually move away as though that it comes from a focus point in front of the lens. Okay, so I think it's syllabus from Form 1. I remember showing this lens to the Form 1s last year. So the light rays from the lens on top will focus onto the white screen below, the bright lines corresponding to the crest, and the dark lines will corresponding to the throw. Okay, so this is one part that you have to be very aware. I think this question over the past 5 years came out one time, but it didn't come out last year. So Form 5 students, please be aware about this. Right, this question sudah lama tak keluar. Okay, so wavefronts. Now, wavefronts is the part that I told you that the textbook go and shifted from 5.1 until 5.3. All right, they taught wavefronts later on. So wavefronts are actually lines that are joining all points vibrating at the same phase, which means what? If I use back the simulation, all right, this bright line is considered as my wavefront. Or if I talk about here, all right, this compression, all right, this compression and compression part, this is also considered as my wavefront. All right, wavefronts are a line that joins all points vibrating at the same phase. Let me get my spotlight. Wavefronts are lines joining all the points vibrating at the same phase and equal distance from the source. All right, so the wavefront of both transverse wave and longitudinal wave are perpendicular to the direction of the propagation of wave. So what does it mean? Okay, so it means that this wavefront, this is the source of the vibration for a longitudinal wave. So there are a few particles, air particles at this position. They are the same distance away from the source of the vibration. They actually are joined by a imaginary line. Right? Wavefronts are imaginary line because it doesn't really exist. It's just that when we see the simulation as though that it's moving away. So these are actually considered as a wavefront. It's an imaginary line whereby it joins all the particles that is moving away from the source of vibration at an equal distance. Okay, so all right. So the wavefronts of both transverse and longitudinal wave are perpendicular to the direction of the propagation of the wave. What does it mean? It means that if the plane wave is moving towards the right hand side, the wave front is perpendicular 90 degrees to the direction of the wave propagation. So if you were to look into this simulation that I showed just now, okay, so my direction of the wave propagation is moving downwards. So when it's moving downwards, it's going towards the negative y-axis. So what is perpendicular, or what is 90 degrees to negative y-axis? That would be the x-axis, isn't it? So these blue lines, all right, blue lines, the bright lines, these are called the wave fronts. Why? Because it is moving perpendicular to the direction of the wave. The wave is moving towards negative y. Perpendicular to negative y is the x-axis. So the white color, the bright fringes, all right, all these lines are moving perpendicular to the direction of the wave going downwards. So these bright lines moving downwards, these are called the wave fronts. So if it's a single source, suddenly it's not moving. Okay. So if it's a single source like this, the wave is moving downwards, it's spreading circular. All right. When it's spreading circular, the wave front, this position, let me just quickly screenshot this. Give me one quick minute. Okay. All right. So if, let's just say, for example, this is the circular wavefront. So the arrows, this is the direction of the propagation of the wave, is moving circular. So 90 degrees to it is here. 90 degrees moving is like this. All right. So this line that connects here, this is called the wavefronts, circular wavefronts. All right. So I hope this explanation does kind of clarify you guys on what a wavefront, circular and plane wavefronts looks like. Right. So wavefronts, they are 90 degrees to the propagation. Circular wavefronts also, it will look like this. The one on the right. Where did my pointer go to? Okay. So even though it's moving in a circular, it is still 90 degrees to the direction of the wave propagation. So these lines are imaginary lines, right? Because it's the same position, distance away from the source of vibration. This is known as the circular wavefronts and the plane wavefronts also. All right. So normally wavefronts are the crest, right? Normally wavefronts are the crest. So PQ, RSTU, and UV, they are considered as a wavefronts. So we normally draw the crest as a wavefronts. So if you recall back the question that I asked you guys to do just now, all right? The same question that I asked you guys to do just now, which is, let's go backwards. This one, all right? So these lines, all these lines is representing a wavefront. Okay, when it represents a wavefront of a water wave, means this is one wavefront, this is the second wavelength. This line is the line is a wavefront. So between two wavefronts is a wavelength. Okay, between two wavefronts is a wavelength. So we have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 wavelengths, and the distance for 8 wavelengths is 12 centimeter. So the wavelength is 12 divided by 8. That's why some of them got 1.5 centimeter. All right, so this is how we determine the wavelength of water wave in the diagram above. So this kind of question, they will normally come out in paper 1, objective questions. Okay, because it's a very simple, you can answer this question within 1 minute. Objective question, you're supposed to answer the question within 1.5 minutes. They will not give you a very complicated question to answer. Okay, so that is one part. Now, can you try this question now? A slinky spring vibrated to generate longitudinal wave. The wavelength of the waves are. All right, those of you who want to join in and try to give your answer, it's over here on the right hand side top corner. That is the class point code. You can see it at the chat box anyway also. So determine, when you see this, first determine the wavefronts. All right, a wavefronts, between the distance between two wavefronts, that's a wavelength. Okay, so determine the wavelength of this wave. This slinky spring vibrate to generate longitudinal wave. Longitudinal wave means an example of sound wave. So Chirong, longitudinal wave crest and crest, or the wavefronts is how one. Very rare that Chirong will get wrong leh. So either my explanation not clear enough, or Chirong not focusing properly. Stomachache. Better careful exam month coming The rest? Still confused, don't know how to do? Okay, I have a few answers that came in already actually. Chong Wei, you never fail to always make me laugh in class Go. This also you have to ask me So as you can see over here, most of them answered. Alright, good. Alright, so how did this answer come out from? So I'm going to show you the working right now. Okay, I'm going to stop the submission. Okay, so how did this answer come out? Alright, so this is one wavefront. The compression area is one wavefront. There's another wavefront here, and a third wavefront is at the end. So for longitudinal wave, the wavelength is actually the distance between two consecutive compression regions. So this is one wavelength, and here is another wavelength. So 40 centimeter is for two wavelength. Therefore, one wavelength is 40 divided by 2 equals to 20 centimeter. Now, if this question comes out in paper 2, all right, so for Form 5, yesterday when we had our technique menjawab, all right, honestly to tell you guys, when I started teaching SPM level, I am aware that there's no marks for the formula, but I still made you guys write the formula. Why? Because if you don't write formula on certain cases, I don't even know what are you trying to calculate. So for me, it is a good habit that you show the examiner that you are very firm and very confirm. What are you doing? Okay, instead of you don't write a formula and then directly write the substitution and the answer and unit. Okay, so for the form 4s, right, yesterday technique menjawab, the speaker actually mentioned that if it's a 2-mark calculation question, the first mark goes to substitution. All right, your working calculation, which means this part, your working calculation here has 1 mark, and then the final answer and the unit has 1 mark. Then all of you, I'm sure in your head you will be saying, why Guan Liang always forces us to write formula? Because if you don't write the formula or the beginning part, sometimes I don't even know what you're trying to do. Okay, I don't even know what you're trying to do. So when does the formula mark is given? When it is not written in the list of equation, the formula is there. But then honestly, to me, I rather train you guys to do the actual proper method. That means you write the formula and then you write the substitution, that means your calculation, and then your final answer with the unit. All right, final answer with the unit, it trains you to remind you to memorize what kind of question, what formula to use, how to use it, the substitution and all. So I am aware that the marking scheme, there's no marks for the formula unless it's not in the list of equation. It's nothing new to me. But I still hope that you guys continue this practice of writing the formulas, all right? Then only substitute the values in and writing the final and the answer and the unit. Because that is one method to memorize the equation, to memorize the formula, and also tells you what you're doing. It gives an impression to the examiner that you are very clear of what you are actually doing. Okay? So I'm sure the Form 5 yesterday learned a lot of stuff lah. So hopefully you guys will share later on what you all really learn. Okay, so let's see the timing right now. Okay, before I proceed this, maybe I'll let you guys go for a quick 2 minutes break before I continue on again. So be back in 2 minutes time. Alright, are you guys back? Or you guys have been staring in front of the computer and also the phone anyway? This is the second part. All right, this is the second part of the wave. Okay, so rupa-rupanya is for Puan Leong to rest my throat lah, huh? Okay, so we're gonna continue on with the graph of displacement against time. Okay, so again back to the simulation just now. All right, this simulation whereby the pencil move up and down. Okay, there's two methods for us to interpret this wave that is being drawn. Okay, so how do we interpret the informations from the graph? Okay, first thing first is a graph of displacements against time. The most important thing, because there's two kinds of graph. This picture is taken from the textbook. There's two types of graph for wave. One is a displacement time, and the other graph is a displacement distance graph. So what is the difference? The difference come on the y-axis. Displacement time graph, not y-axis, the x-axis. For displacement time graph, the x-axis is time. So after a certain period of time, after some time taken, all right, where's the position of the particles or the position of the wave? And then for the other one is a distance. Distance here is from how far it is from the source of the vibration. Okay, so this is one of the questions that the calculation questions or the graph questions that they ask in wave chapter. So let's see about graph of displacement against time. A graph of displacement against time means the displacement unit in x centimeter, and then the x-axis is time unit in seconds. So it's very important for you to identify what is the unit at the axis. All right, because if they change the unit, then you kantoi already lah that time. Okay, so from what are the information can we get? First, on the x-axis, it is also the equilibrium position. Okay, on the x-axis, that is also the equilibrium position. So from the equilibrium position to the maximum crest, or the equilibrium position to the minimum position, that's the amplitude. Okay, so amplitude means from the x-axis to the max point, to the peak, or from the x-axis towards the minimum point throw, that is amplitude. Now, that is what we can get from y-axis. So what information can we get from x-axis? The information that we can get from x-axis, because this is a time on x-axis, so the information that we can get is period. Remember, recalling period is the time taken for one complete oscillation. So one complete oscillation could be anywhere. It could be from the crest, going down to the other maximum position and going back to the top again. So that is time taken for one complete oscillation known as period. It doesn't matter whether it's from 0 to max 0, mean 0, as long as it has to reach two extreme ends. Okay, so displacement time graph, first information we can get is the amplitude. Second information we can get is period. And then we get the frequency by dividing 1 over the period, we can get the frequency. So for a displacement time graph, we can get three information: amplitude, period, and frequency. All right, this is for displacement time graph. Next is from displacement distance graph. Displacement distance, because the y-axis is still displacement, so the only information we can get from y-axis is from the equilibrium position to the max, or the equilibrium position to the minimum position. That is the amplitude. All right, distance of the distance from equilibrium position to the max point or to the minimum point. The second information that we can get from a displacement distance graph is the wavelength. The distance for the wave to complete one oscillation from the crest to the consecutive crest to the next crest, that is the wavelength. Okay, so that is the two informations we can obtain from a displacement distance graph. Okay, so I'm gonna go next, and I think that's the exercise, and my class point is going to appear, but don't answer that question yet, okay?
Wait, Chair, before you go, can you go back to the displacement time graph? I just want a screenshot.
It's in your textbook, Rebecca.
Oh, okay.
It's in your textbook. It's just that I kind of make it bigger only. I took this from your textbook. I merged this slide that I'm doing right now is I merged my previous KBSM syllabus with the textbook. So that's why there are some things that is inside your textbook and some are not. Okay, so can I proceed?
Yep.
Okay. All right. This one, okay. All right. This question, I'm gonna show it to you all first. Okay. Weird that the class point didn't start. Now mind. So I'm gonna show you how to do this question first. This is a circular wave produced by a vibrating spherical dipper. All right, with a frequency of 5 hertz. So this is a wave front here. Okay. This is a wavefront. So again, the distance between two wavefronts are known as a wavelength, lambda. All right, so that's one wavelength. This is the second wavelength, third wavelength. The original source, okay, as you can see, I don't have to go any deeper because the 4.5 centimeter is from this position up to the outermost position. All right, so the question asks what is the wave speed? Wave speed formula is F lambda. So the frequency is already given to us 5 hertz over here. So we have to in order to find the wave speed, we have the frequency. We want to find the wave speed. So we have to calculate what is the wavelength. All right. So 4.5 centimeter is actually for 3 wavelength. So lambda equals to 4.5 divided by 3. That will be 1.5 centimeter. All right. So this is one wavelength. Then using the formula of V equals to F lambda, the frequency is 5 hertz, multiplied by wavelength 1.5. Now, some of you will be asking me, teacher, the wavelength is in centimeter right now. Do I have to change it to meter? Now, in the sense of this situation, you want to change also can. You don't want to change also is okay. But make sure when you calculate this, where's my calculator? Can someone calculate for me 1.5 times 5?
7.5.
7.5, thank you. All right. So when I write 7.5, you have just to remember that your wavelength is centimeter. So the wave speed is centimeter per second. Do you have to change it to meter per second? Not necessarily. You can leave the answer as centimeter per second. Okay, you don't have to change it to meter per second. Unless the question asks you to change back to its SI unit. Or else no need to change it to meter per second. Okay? Right, let's go next question. Right, determine the wavelength and the amplitude. I'm just very curious why my pass point not working. Okay, very quickly because I want you guys to try to do the questions. There. Alright, can you please try to do this question? Curious, can you guys hear the background music? Is it
No.
all no? Okay.
No.
Alright, Chirong's question is it always centimeter per second? Wave speed is normally distance over time. So sometimes it's centimeter per second, it can be millimeter per second. You have to look at the question, no? Okay, Chirong? So the question right now is determine the wavelength and the amplitude from the graph below. So this really tests you guys. If you all cannot do, just tell me you all cannot do. It's still practice anyway right now. I think amplitude wise you all can do. I guess you're stuck at wavelength. It's better to get stuck in class than getting stuck in exam. So if your question is, will this type of question come out? Probably. For paper 2 also still can probably. Paper 1 also possible. Nicholas, good job. Rabika, correct. Brian, wavelength salah. Darren, wavelength salah. Whoever Chi Chi is, wavelength betul. Correct, good job. Navin, sorry, answer is wrong. Li Ching, good job. Alright, I'm gonna close submission over here. Okay. Chirong, I thought Chi Chi is a girl, you know, because I have a friend named Chi Chi. Okay, now, amplitude, all of you got correct. The 7 students who actually submitted in amplitude wise, you all got correct because amplitude is from the equilibrium to the max position, A, and then from equilibrium to the minimum, that is also A. So you have 2A equals to 5 centimeter. So A equals to 5 divided by 2. Please show 5 divided by 2. Okay, I know some of you will have a tendency to do 2A equals to 5 and then A equals to 2.5. For your information, the marks is given here to see 5 divided by 2. Alright, so you get 2.5 centimeter. So if it's a 2 marks question, then they will give here 1 mark, here 1 mark. In physics, we do not see the final answer correct, we give full marks. Even for mathematics nowadays also you have to see the examiner wants to see the working. You don't show the working, you get the final answer with the correct unit also, no point. You only get 1 mark, you won't get the full marks. Alright, so this is getting for amplitude. Now wavelength, how to calculate the wavelength. So I'm going to show you my method of calculating. Now wavelength here means from the crest to the crest. This is a wavelength. Okay, so this is the wavelength. But then the problem right now is the question gave you from this position until this position, it's 18 centimeter. So what I do is, I break this because here is the additional part. This is one part, alright, of a wave. And if you notice, it's half of the other one. Alright, this is one of it. If I split the wave again, there's 1 portion, 2 portion, 3 portion. Okay, so 2 portion of the wave is a wavelength. So how did I calculate the wavelength? So I calculated 18 centimeter. Okay, the wavelength is 18 centimeter times 2/3. Because there's supposed to be 3 portion, but a wavelength is only 2 parts of it. So 18 centimeter times 2/3, This is my maths using mathematic method to solve the question. So that would be 12 centimeter. Okay? Because I split the 18 centimeter into 3 parts of the wave. And wavelength is only 2 parts of it. Okay, so I'm using a mathematic type of method to solve this question of mine. All right, so I'm going to go to the next question. Try to do this now. This one should be much more straightforward compared to just now. Xinyan, the x-axis is time. Wait, let's see. While the rest is doing this question, I'm going backwards on my slide. Xinyan, I think it's typo error lah. Thanks for informing Reed that. I think it's typo error. Thanks for identifying that, but then you should have informed me just now. I didn't even notice myself. Alright, so far there's 3 person who submitted in already. Xinyan, good job. Darren, Li Cheng, I would do appreciate if I can see some working on how to do the question. That's why it's an image upload. The rest? I think I have 4 person. Another answer came in from Nicholas. The rest still doing it. 新明, your wavelength is wrong, 新明. Chirong, your answer is correct. Good job. If you hear background sound, do ignore it. IU how to get wave speed. Wave speed's formula is V equals to F lambda. V equals to F lambda. So far, we only have two formulas in this chapter right now that we learned so far. V equals to F lambda is the first formula. The second formula is frequency equals to 1 over period. Rabika, good job. Correct. Chuyang just sent in. Chuyang, your answer is correct, but you don't have to find the period. Okay, I'm going to close submission already. Now, okay, so let's see. Let me take Brian's answer. Okay, so wait let me just put this out first. Okay, so how do we actually calculate the answers? Number one, from the x-axis up to the maximum position, that is our amplitude. Or from the x-axis down towards the minimum position, that is also the amplitude. So the amplitude, right? Question A, how you're supposed to answer is from the graph amplitude A, you can just write A equals to 10 meter. That's it. All right. And then B, please do make sure if this is a paper 2 questions, all right, always label A and B. Do not hand in your answer without labeling what question you're doing, right? Not even for physics, but other subject also. I heard that in Sejarah, if you do not label, you directly get 0. Okay, so please make sure you label them. The next part is the wavelength. Now, Xingming, please take note on here. A wavelength means wavelength is the distance for one complete oscillation. So from the equilibrium position to the maximum, to the equilibrium position to the minimum, and then back to equilibrium position back again. This is known as a wavelength. All right. So the wavelength could be crest to crest, throw to throw, equilibrium to equilibrium. But how many complete oscillation here? Here from crest back down here, this is 1. All right. And then going up and down again, this is second time. Okay. So which means we have one wavelength and then another wavelength. So actually we have two wavelengths here. 2 lambda equals to 2 meter. Lambda equals to 1.0 meter. Okay. So this is how you do the working. Next is part C. All right. Part C, we want to find wave speed. So I would suggest you guys one thing. I saw some of your working. Try to put the information first, then only write the formula out. So information, what do we have? We have frequency, 8 hertz. All right. We have wavelength calculated in front already. So V equals to F lambda. Frequency is 8. Wavelength is 1. So answer is actually 8 meter. All right. So remember, all right, this formula is actually shown inside the list of equations, so there's no marks given for here. But again, I would appreciate if you guys write that out as a practice for you guys to memorize the formula. And then I need to see the substitution, that's 1 mark. And then 8 meter, 1 mark. Okay. So like for example, Shinya, I'm going to take your example to show out. All right. So for Shinyan's this part, she did the formula. And then she put F equals to 8 hertz here. And then I was staring at her working for quite some time because I see V equals to F lambda, 8 hertz, F, and then suddenly 1 times 8. So the flow is like a little bit kelangkabut. So make your flow better, Xinyan. Alright, so the rest I think shouldn't be much of a problem. Okay. So one last question before we end today's lesson. This is quite a very fast question. I became blur teacher at that question. Which question? Just now that question, Nicholas. Later I show. Let me finish this question first, then only I go back and see your working. Nicholas, it's okay. It's practice now. It's not the actual exam. Most importantly, it's not SPM. Determine the frequency of the wave. So this is a displacement time graph. X-axis, you can determine two things, period and frequency. But in order to get frequency, you have to use a formula. Xingming, answer in physics cannot be in fraction. Xinyan got two working on %. And Xingming, unfortunately, they say your working sudah salah. Xinyan, unfortunately, they say your working also salah. Li Cheng, your working also salah. I see who can get this question correct. My two top student from Omega and Alpha pun sudah salah. Let's see who can get it betul. Chong Wei terbalik. Chong Wei question mark, question mark, question mark. Ayo, Chong Wei. The rest? Xinyan and Xingming, if I'm not wrong, you can resubmit you know. Rabika, I'm waiting for your answer. I want to see whether can or not.
Wait, answer. Hold on.
Xingming cannot resubmit meh? Technically, I remember can resubmit. Ray, sorry, wrong. Brian, sorry, juga salah. Mr. Chichi, salah. Lorraine, sorry, wrong. Xiang, wrong. Okay, I'm gonna close submission. I noticed no one noticed the reason.
Wait. Che. Wait. I'm trying to download the photo. It's very hard download the photo, Che.
Finally, someone got it correct. Chongwei, not 6 hertz.
Che, so the answer is 2 hertz?
Nope.
It's not? Oh my god.
Harshini also wrong already. Alright, I'm gonna close submission already. Unfortunately, the answer is Xinyin got it correct the second time. 2000 hertz. Why? Millisecond. Period. There's 2 period here. This is the first period. And this is the second period. So 2 period equivalent to 1 millisecond. Milli is 10 to the power of negative 3 second. So T is 5 times 10 to the power of negative 4 second. Frequency formula is 1 over period. 1 over 5 times 10 to the power of negative 4, we get 2000 hertz. Kan I dah kata, be careful with the unit. No, Navin. This is time. I wouldn't put meter times second. Alright, so it's actually millisecond. Okay, so be very careful with that. Alright, so I think I'm gonna stop here for today. Damping and resonance, I'm gonna talk about it next week. Okay, so so far any other questions? Let me go back and see Nicholas when you're working. Do not overcomplicate yourself with the question. New quotes from me, huh? I want to see Nicholas working. Mana Nicholas when you're working. Ayoyo. Okay, Nicholas, you forgot. You need to relearn this video again. Amplitude is just from the equilibrium to the max. Okay. Moral of the story is be careful with all the simple stuff. Okay? So I guess I am going to stop here today. Any other question? Can I see question C answer? Nah? Actually, you can see my working down here. That's the answer for question C. So the rest of you, that's all for today. So if there's no other things that you want to ask me, you can actually leave the chat Google Meet already.